Welcome to this session of lecture on the radiation from a magnetic current source in a homogeneous medium. We will be computing the spherical wave components due to the magnetic current source. So, let us draw the x, y, z coordinates for this problem. This is x, that is y, and that is z, and we have a magnetic current source the magnetic current source has a magnetic dipole moment K L . Okay. This K is capital, not to be confused with the propagation constant, which is small k, and it is placed at the origin. So, because the current is z directed, the magnetic current source is z directed, F will also have a z component only, and therefore, the Helmholtz equation can be written as grad square f z plus k square f z is 0. So, we call this equation 10. Also, due to the spherical symmetry of the problem, also the fields will be spherically symmetric due to the nature of the problem. So, let us express f z as a function of the radial coordinates f z r, and therefore, equation 10 can be rewritten as, in the nomenclature of the spherical wave components, grad square f z r plus k square f z r equal to 1 by r square del r r square del f z r del r plus k square f z r, and that will be equal to 0. Again, this differential equation has two independent solutions given by f z 1 equal to C 1 e to the power minus j k r by r, and f z 2 equal to C 2 e to the power j k r by r. We call this equation 11, we call this equation 12, and we call this equation 13. So, this is the equation of a forward going wave or an outward going wave. This is So, this is the equation of an outward travelling wave, while this is the equation for a inward travelling wave. So, because the dipole is radiating and it has to obey the radiation condition, we will take the solution to be f z 1 . The solution f z 1 also vanishes at r is equal to, the solution f z 1 also vanishes as r tends to infinity. Therefore, we choose f z as C 1 e to the power minus j k r by r. Now, as k tends to 0, equation 7 reduces to the Poisson's equation. For which the solution is f z is equal to k L by 4 pi r. This k is a capital K. Therefore, our constant C 1 must be equal to k L by 4 pi, and therefore, f z will be equal to k L by 4 pi r times e to the power minus j k r. This is equation number 14. So, this is again the equation for a spherical wave. Since the surfaces of constant phase are spheres, so this is the equation of a spherical wave. Since the so this is the equation of a spherical wave, since the surfaces of constant phase are spheres, then we compute the electromagnetic field radiated by the magnetic current source by substituting equation 14, the expression for f z, into the original equations which enable me to calculate the electric and magnetic fields due to a magnetic current source, which are equations 8 and 9. So, by substituting 14 into equations 8 and 9, we can calculate the electric and magnetic fields radiated by the magnetic current source. So, first from 8, we have E equal to minus curl of f that is equal to minus 1 by r square sin theta a r r a theta r sin theta a phi del del r del del theta del del phi f r f r r f theta r sin theta f phi. Again referring to the diagram we drew before for the relationship between the rectangular coordinates and the spherical coordinates. For the case of the electric current source, you refer back to the diagram. We will have f r equal to f z cos theta, f theta will be equal to f theta will be equal to minus f z sin theta and f phi will be 0. Now, all we have to do is to substitute these here and calculate the value of the electric field. So, the electric field will be equal to 1 by r square sin theta a r r a theta r sin theta a phi del del r del del theta del del phi f z cos theta minus r f z sin theta 0, that is equal to minus 1 by r square sin theta a r 0 minus 0, because there is no variation with respect to phi, plus r a theta 0 minus 0, again because there is no variation with respect to phi, plus r sin theta a phi del del r minus r f z sin theta minus del del theta of f z cos theta and that becomes equal to minus 1 by r square sin theta r sin theta f I times, now you substitute for Z del del r of minus r k L by 4 pi r e to the power minus j k r into sin theta minus del del theta of k L by 4 pi r e to the power minus j k r into cos theta. So, that becomes equal to one by r k L by 4 pi f I minus j k e to the power minus j k r sin theta minus 1 by r e to the power minus j k r sin theta. And that eventually works out to E phi equal to minus k L by 4 pi e to the power minus j k r j k by r plus 1 by r square sin theta as the phi component of the electric field with ER to be 0 and E theta to be 0. So, therefore, the radiated electric field will only have a phi component with the radial component of the electric field 0 and with the elevation component or the theta component of the electric field also to be equal to 0. So, we can call all of them So, we can club all of them into equation 15. So, let us stop here. We will next calculate the radiated magnetic field components by the magnetic current source. Thank you.